In this video, we're going to deduce the structure using NMR of C9H10O. So here is the NMR, and I'm going to point out some important things before we move on to the table. And it's always good to look at the NMR with your kind of watchful eye first. So first of all, we've got an oxygen in our molecule, and start thinking about what functional groups you could have if you've got an oxygen in the molecule. One of them is an alcohol. So if we look here, can you see a singlet with a 1 anywhere here? That's an alcohol, a singlet with a 1. No, I can't. So there's no alcohol. It's not an alcohol. The other one that contains 1 oxygen is aldehyde. So on your data sheet, hopefully you're looking at a data sheet now, you can see between 9 and 10 is your aldehyde peak. Can you see something between 9 and 10? No. So actually one of the best things about NMR is to eliminate what is not there first. So we know no aldehyde, no alcohol. Okay. With any other one with an oxygen, just 1 oxygen, is a ketone. So let's have that in our mind and keep that in our mind. There might be a ketone. Okay, we've got a CH2 and we've got a CH3 here because of our relative peak areas. But they're next to a carbon with no hydrogens on. So we know the carbon next to these two peaks has no hydrogens on. We think it's a ketone, and we know that about these two peaks. We can see we've got a benzene peak right here, and we know it's mono-substituted because of the 5. Let's do the table. Chemical shifts. Notice we've got a range for benzene. We don't have to give it a precise chemical shift. We can just give a range. Okay, and then we do the peak splitting. Multiplet for benzene, remember, and then your peak areas 3, 2, and 5. We then go for our different hydrogen environments, and then explain the n+1 rule, just to get into that rhythm of explaining it at least once every time. So n+1 equals 1, because we've got a singlet, and so 1 minus 1 equals n, which is 0. So that means they are next to carbons with 0 hydrogens on them, which we've already mentioned. Now, if we start to have a guess as to what these are. So first of all, we think this might be CH3 because of the relative peak area, that might be a CH2 because of the relative peak area. We think that might be benzene. We're sure that's benzene because that's all that appears in that area. If we then look at this as well, we notice if you look at the data sheet can make it more confusing. If you look at the data sheet, this could be next to a C double bond O, and this could be next to a CO. Now you can't have a C double bond O and a CO in this molecule, so therefore the data sheet, even though it's good sometimes, can sometimes also be very confusing. And remember, also the benzene pulls these peaks downfield sometimes. So that means this peak is more likely to be next to the benzene than the further one away. Okay? Now, I'm going to teach you the next trick of doing this. You're given a molecular formula. So sometimes it's good to write down what you think it is. Okay? And as long as it's unambiguous, this will still get you marks, by the way. It doesn't matter what. You have to put this so it's unambiguous. That's all. As long as they can tell exactly what hydrogen you think gave the peak, that's fine. So take the molecular formula and then minus these away. Now that leaves you with CO. Now if we then take the table, put it up there and leave our CO there, and we start to actually work it out. So we know we've got a CO. Now CO, okay, next to a benzene. So let's draw the benzene. There's your benzene. You know it's mono-substituted. We've already said that. It's mono-substituted, which means there's something coming off there. Okay. We know there's a CH2, we know there's a CH3, and we know there's a CO. Now, in terms of bonding, if we say there's something connected to here, we know there's no hydrogens on this carbon because something is bonded there. We just don't know what one it is. Now, it would make sense because it can't be the CH3. Okay, it can't be the CH3 because that's a terminal. Okay, it's got to be the CH2. So if I put my CH2 there and start testing it out, okay, so I put a CH2 there. Right, that makes sense. Then I can't put the CH3 because then I don't have CO in there. So let's put CO in. Okay, and CO, you want 4 bonds to your carbon, it can only be like that. Now, if that is the case, CH3 goes on the end. Now, if we go back through this and we say, well, let's just check. So you always do a check if you're right. Okay, and we've just connected this up. There's no hydrogens on that one. There's no hydrogens on that one. And therefore, this would be a singlet. There's no hydrogens on this carbon next to here, so this would be a singlet. Okay. This one would be a multiplet, and a multiplet with a relative peak area of 5. This would have a relative peak area of 2, relative peak area of 3. Now I want to show you what mistake you could have made. So you could, for example, start filling around and start doing this. Because it's all about how this jigsaw puzzle fits together. So you could put CH2, sorry, not CH2, CO, and then CH2, and then CH3. CH2 and CH3. So that's the other way. And could all we've done is CH2, CH3. So let's think about why that would be wrong. Sometimes it's good to, your initial guess might be wrong. So if we look at that, that is next to two hydrogens on that carbon. So 2 plus 1 equals 3. So that would be a triplet. Okay. That is next to 3 hydrogens, so it would be a quartet. So the more used to it you get, the more you realise, draw something, go through it and say, right, okay, I can't see a triplet in a quartet. Can't see a triplet in a quartet, and therefore that definitely is wrong, okay? So that is wrong. So go through it and check it, just like I did. I drew this, thought it might be this, then I drew it and went through and checked it was right. So I know full well that this one is correct, okay? And so that is how you use benzene and you find out you've got a ketone. To summarise our learning in this NMR, first of all, we used the relative peak area to deduce how many substitutions there were, and they had 5, so we knew it was monosubstituted. Once you've deduced the groups, subtract the atoms away to find out what's remaining. Like I said, if it's CO, it's usually a ketone, and there's our ketone that we've drawn, okay, and there's our calculation that we've done. And we'll do that time and time again over the next few examples.